Assalamu alaikum. Today's lecture is about
line compensation. Right? We already know that at surge impedance loading, the surge impedance is resistive. Surge impedance is resistive, and the load is surge impedance load means it is also resistive. So if both surge impedance and the load both are resistive, there is no reactive power flow. Along the line. And if there is no reactive power flow, the voltage at the sending end and the receiving end, they are equal. So the voltage profile is constant. So now if I have to draw it like this, for example, we have a 500 kilovolt line, and on the x-axis we have length of the line, and if the length of the line, with the length of the line, it does not have any impact. So this line actually represents the surge impedance loading line. So the voltage remain constant with the increasing length of the line, right? So if the loading is less than surge impedance loading, so what will happen? The voltage will be greater than the sending end voltage that we explained in the Faraday effect. When the receiving end current is 0 or it is a very small value, we will have a VR which is greater than Vs. So this is the graph for loading less than surge impedance loading. And if it is greater than surge impedance loading, so it will be decreasing. So the voltage will be decreasing towards the receiving end. So this graph is for loading greater than surge impedance loading. So there is a voltage drop in case of loading greater than surge impedance loading. So what do we want is that we want a constant voltage profile or somewhere closer to this constant voltage profile, right? So it should not be exactly equal to this straight line, but it should be closer to that. We don't want excessive voltage at the end, at the receiving end, and we also don't want the voltage level very low at the receiving end. To remove these two problems, we usually use compensations. And we have shunt compensation, in which we can attach a reactor, which is actually an inductor, or a capacitor at the receiving end. And then we have a series compensation. In which we attach a capacitor in the middle of the line in series, middle of the transmission line. So starting from the shunt compensation, there are two cases. The first one is voltage rise. So this occurs when the loading is less than surge impedance loading. And to remove the voltage rise, what we do, we actually attach a shunt reactor at the receiving end. What does it do? It increases the reactive power flow reactive power flow in the transmission line. And what does it mean that the reactive power flow is increased? The current flowing from the sending end towards the receiving end, it has actually two parts. One is the real part, and then we have a reactive part. So if you will attach a shunt reactor at the receiving end, this IQ will increase, right? Because you need more reactive power at the receiving end, so the current will increase. So if the current is increasing, the voltage drop across the series impedance will increase. So if voltage drop will increase, so the receiving end voltage, which was higher than the sending end voltage, it will come closer to the nominal value, the straight line profile. So it will maintain the voltage profile by reducing the voltage at the receiving end. So this was the voltage rise case. Now if we have a voltage drop at the receiving end, so for voltage drop, it occurs when the loading is actually greater than surge impedance loading. So we apply a shunt capacitor at the receiving end. And what does it do? It provides the reactive power that is required by the load at the receiving end rather than fetching it from the sending end, right? So the reactive power does not have to flow through the transmission line, it is being provided at the receiving end. So what will happen? That it will decrease the reactive power flow. Through the transmission line, because the capacitor provides the reactive was that are needed by the receiving end load or receiving end terminal. So these are being provided by the capacitor, and we don't have to fetch it from the sending end. So in this case, IQ from the transmission line, that decreases, so the total current decreases, and if the current decreases, so the voltage drop decreases across the line impedance. So what we are doing, we are maintaining the voltage profile closer to the straight line. We are increasing the voltage at the receiving end. So these are the two shunt compensations. The third one is the series capacitor or series compensation. I will write it series compensation. So this series compensation, we are actually attaching a capacitor at the midpoint of the transmission line. So we are adding a series capacitance at the midpoint. Of the transmission line. And what does it do? It increases the stability of the transmission line. And also increases the power transfer capability. Now if you remember, for the transmission line, for the short transmission line, we actually derive the formula for the real power, that was equal to VSVR sine sigma over x, right? So this is the formula for the real power at the sending end. So if I will add a series capacitance at the midpoint of the transmission line, then I will have another quantity in the denominator, which is the capacitive reactance. So this value will become small because we are subtracting the capacitive reactance from the total inductive reactance, and this will increase the power transfer capability. Because the denominator is becoming small, so the overall fraction will give you a larger value than before when we only have a inductive reactance. Now we have added a series capacitance with the inductive reactance, so the denominator has decreased and the power transfer capability is increased. So that's why we use the series compensation to increase the stability and also to increase the power transfer capability.